Hello everyone, welcome back to another lessons learned video. Today we're going to practice doing some resonance structures. So go ahead and try to draw the resonance structure for this molecule here. So the double-sided arrow here means that whatever we're going to draw on the right side is a resonance structure. Now, the way we can show it is that we know that there are two lone pairs on the oxygen atom, and we know that they're going to move, not necessarily move, but we can show them moving to form a pi bond between the oxygen and this carbon. Then the pi bond electrons here would have to move to this carbon. If they were to stay here, we would have 5 bonds around that carbon, because we would have 1, 2, 3, 4, and then we would have also the this bond, which is 5. So that would not work. You can't have more than 4 bonds around a carbon. So this is what we end up with. So to be clear, when we mean resonance, we don't mean that the electrons actually move here. They don't actually move. It's just that the molecule is in both states at the same time, right? The molecule is, in other words, these electrons aren't necessarily here or here. They're kind of in between. So in reality, this carbon doesn't have a full negative charge. It has a partial negative charge, because in the other resonance structure, it's got a neutral charge, and this oxygen is partially positive. Now go ahead and try this problem here. So in this situation, one of the or two of the electrons in this pi bond, the 2 electrons in this pi bond are going to, we're going to show them as going to the oxygen, and then 2 of the electrons here on the oxygen are going to come in and form a pi bond to the carbon. You can also show this, if you don't show all the lone pairs, you can show the arrow coming from the negative charge that shows a lone pair going there. So what we get is this right here. So now to show the third resonance structure, we can move electrons, a lone pair from this oxygen, form a pi bond here, and then move the pi electrons here to the oxygen. So what this shows is that there's a -2 charge on the entire molecule, right? There's a 1 charge here, 1 charge here, and that -2 charge, the 2 negative charges, are being distributed equally among 3 oxygen atoms, right? So that's the meaning of resonance. It doesn't mean that the electrons actually move here and become this. That doesn't happen. So go ahead and try the resonance structures that you could draw here. So from this situation, we know we're mostly going to be interacting with this positive charge. And we know it's allylic because there's a pi bond here, and one carbon away from the pi bond, we have this positive charge. So in order to show what would happen, the pi bond electrons can move over to this bond, and then the result of that will be that we are going to get a resonance structure so the pi bonds are coming here, and so because the two electrons move to this carbon, to this bond, this carbon is unaffected, right? Because at one point the electrons were slanted to the left, now they're to the right. However, this carbon here is losing electrons because they're moving away from it. So that carbon is going to have a deficiency of electrons, also known as a positive charge now. And this carbon is having new electrons added to it, so it's going to lose the positive charge. It's going to become neutral. So here it's neutral. Now here, a similar sort of thing would happen. We have a pi bond that is that has a positive charge allylic to it. So these electrons can move closer to that positive charge. So this is no longer here, but it's actually over here in the positive charges on this carbon. You can conceptualize maybe the positive charges moving two carbons each time. So it moved from here, two carbons, so now it's here, and now it moves two carbons, so now it's here. Although what's moving is not a positively charged particle, it's just electrons moving in the opposite direction. Now at this point we can have two things happen. So let's delete what we have on top so we have space. At this point we could either have the positive charge interacting with either these pi electrons or these pi electrons. So let's show this first on the bottom. So these electrons move here. The positive charge is moving two carbons, so it's on the terminal carbon here. Now this wouldn't be a very high contributing resonance structure because the carbocation is on a primary carbon. That's usually not very stable. So that's what would happen if we, let's show this as blue. So this is what happens if we do the blue arrow. If we do the, let's do a gray arrow as well. If we do this, what would happen is that these pi electrons are now here, so then the positive charge moves up here. Now this molecule can also still resonance because there's an oxygen next to it, next to the positive charge. So what could happen is that this oxygen has some lone pairs. They can move toward the positive charge. So you can get a resonance structure, again, that looks something like this. So there's a bond between this carbon and the oxygen now bears the positive charge. It's got only one lone pair. Now, if we were to look at this, these four molecules, this one, this one, this one, and the one on the top left, which one would be more stable? Can you try to rank them based on stability? So there are a couple of trends that we can notice. In all of them, there's a positive charge somewhere. However, the positive charge is on different atoms. So in the example that is over here, the positive charge is on a tertiary carbon. So it's on a tertiary carbon. So the carbon is attached to three other carbons. So one carbon is attached here, two here, three here. Right. In the scenario on the bottom right, the positive charge is on a primary carbon. It's only attached to one other carbon. Here it's attached to a secondary carbon. It's attached to an oxygen, but you can still, it's still an atom there. And it's attached to another carbon there, so it's two. So that's a tertiary carbon that it's attached to. And then the positive charge in the top left is on an oxygen atom. Whenever we have a positive charge on a carbon atom, we're always going to be missing a full octet. The reason is, if I expand this out, for example, notice how I have 2 electrons here, 2 here, and 2 here, right? That means we have a total of 6 electrons. But in order to follow the octet rule, the atom has to have a total of 8 electrons around it. But the carbon doesn't have any lone pairs either, so there's only 6 valence electrons. So this would not be following the octet rule. Whenever we're not following the octet rule, we're always going to be less stable. If you compare this to the oxygen situation that we have here, if I were to expand again, look at it zoomed in, the oxygen has a lone pair of 2 electrons. It has a bond to the right there and 2 bonds to the left. So here it has 1, 2, 3, 4, 5, 6, 7, 8. Right here it has 8 electrons, so it is following the octet rule. So notice the trend, right? Whenever you have a positive charge on a carbon, whether it's tertiary, primary, or secondary, it's always going to not follow the octet rule. But if you have it on a nitrogen atom or an oxygen atom, it's going to always follow the octet rule. So in general, positive charges on non-carbon atoms are going to be more stable. So therefore, this molecule here is going to have number 1 in terms of stability. So this is number 1 in terms of stability. Now we're left with 3 carbocations. We're left with a tertiary carbon having a positive charge, a secondary carbon having a positive charge, and a primary carbon having a positive charge. So which one would be more stable? The trend that you need to keep in mind is that tertiary carbocations are going to be more stable than secondary ones, and those are more stable than primary ones. Primary ones are very unstable. So that's how we rank the stability or the significance of the resonance structures. What this really means is that the molecule is more similar to this than it is to this, right? There's still a very slight positive charge on this carbon atom, but not very much. But there's a much stronger partial positive charge on this oxygen atom. So the positive charge is more spread out more towards the oxygen and this tertiary carbon than it is on the primary carbon and the secondary and this secondary carbon, right? So that's how you should conceptualize it. So sorry. Okay. Deleted everything now. All right. Let's see if we can get some good examples. So another simple example is this one here. So go ahead and try this one. So here, again, one of the lone pairs on this carbon with a negative charge, this oxygen with a negative charge, can move and form a pi bond here. Some of the pi electrons can move up to the oxygen. So the resonance structure we get is going to look like this. So I want you to pay attention to what this actually means. This means that in this molecule, the negative charge is spread out among two oxygen atoms. It's spread out among this one, and then on the other resonance structure, it's on this one. It's partially on one carbon and partially on the other carbon. Now this is pretty significant for a very specific reason. Let me erase the second resonance structure to show you something. And let me also erase the mechanism thing we drew. If you ever heard of a carboxylic acid functional group, it looks something like this. Notice that the molecule we have on top is essentially a carboxylic acid that has lost a hydrogen atom. So if this hydrogen atom were to leave somehow, or something were to come take it, and the electrons were to join the oxygen, you would get this outcome. So this is what you get as a result of a carboxylic acid being deprotonated, or having a hydrogen taken away. So the result is still a relatively unstable molecule because there's a negative charge there, but because it's spread out among two oxygen atoms, which are very electronegative, it's going to be stabilized. It's going to be more stabilized than if it was just on a single carbon atom. So that's why carboxylic acids like to give away this hydrogen, or don't really mind giving it away as much, because the outcome isn't too unstable. It's stabilized by resonance. That explains why these molecules are acidic and they like to give away hydrogen. So for our last example problem, let's go over a pretty big, not big, but it's going to have a lot of resonance structures, let's just say that. I drew it wrong. Let's go ahead and try this one. So in this scenario, what we can have happen is that the pi bond electrons from the benzene ring can move up to form a pi bond here. And if we do that, notice that this carbon has an invisible hydrogen, which we haven't drawn. If we do this, we would get 1, 2, 3, 4, 5 bonds on the carbon atom, which is not allowed, right? So to compensate for this thing coming in here, we got to offload some electrons off of this carbon. So we're going to offload these pi electrons and move them to the oxygen atom. So as a result of that, what happens is that there's now a pi bond here. The oxygen has extra electrons, so now it's negatively charged. And notice that because this is negatively charged and we haven't taken away or given protons, there has to be a positive charge somewhere for the principle of conservation of charge. And it's going to be on this carbon over here. Because as you notice in the mechanism that we showed, the electrons are moving away from it, right? This one. So it's going to leave behind a trail of positive charge, in a sense. Now here you can recognize the pattern pretty easily. So the pi bond can move here, and so the resonance form looks like this, and the positive charge is going to be 2 carbons to the right. 2 carbons counterclockwise, right? Like this. Now here, again, the pi bond electrons move over here. So you can see that it goes back to what it was originally, or similar at least. The only difference being that the benzene ring electrons are kind of rotated. So I hope that video was helpful, and thank you for watching.